Hi, welcome back. Dr. P here again, and in this lecture we're going to take a look at equilibria and rates of organic reactions, or well, reactions in general, and the factors that affect them. Equilibria is affected by thermodynamics and rates are affected by kinetics. So let's take a look at thermodynamics. And thermodynamics involves looking at the energies of the reactants and the products. And thermodynamics will measure the extent of a reaction. And we will often refer to this extent of reaction as equilibrium. So let's say we had the following reaction. So this is simply the reaction that we saw last time. It should be HBr. Oops, there's no plus there, sorry. We just have the one product. Now we can write an equilibrium constant for this, and the equilibrium constant will be denoted with a capital K and subscript EQ for equilibrium. Now equilibrium constants, as you may remember from Chem 1b, can be written as an equilibrium expression, which is the equilibrium constant equals the concentration of the products, so H3C, CH2Br, raised to the powers of their coefficients. So in this case, our coefficient is just 1, so this would be to the 1 power, so I'll leave it blank. So we have concentration of products raised to their powers divided by concentrations of reactants raised to the powers of their coefficients. And at a particular temperature, there's going to be a given equilibrium constant for a given chemical reaction. And in this case, our equilibrium constant is 7.1 times 10 to the 7th. Now what does that mean? Well, one way I like to think of it is at equilibrium you have 7.1 times 10 to the 7th times as much product as you do reactant. So your relative amount here is this is 7 times 10 to the 7th, and these are 1. So you have roughly 70 million times as much this as you do this other stuff. Now we can convert that into an energy associated with the reaction. And the way that that's related is by delta G, or we'll call it delta G naught, assuming we're at standard conditions. And this is our standard free energy change, delta G naught. And that equals minus RT times the natural log of KEQ. So R is the gas constant, 8.314 joules per mole Kelvin. T equals the Kelvin temperature. And then you would plug in your equilibrium constant and take the natural log of it. You could write this in an exponential form as well, instead of a logarithmic form. KEQ equals e to the minus delta G naught over RT. And this gives us our relationship between free energy, so the energy difference between products and reactants, and equilibrium, so our relationship between free energy and equilibrium. Okay. Now, there's another aspect of our energy that we need to take, our free energy that we need to take a look at as well. And that's given by the following equation. Delta G naught equals delta H naught minus T delta S naught. So delta G naught is our change in free energy. Delta H naught is our change in enthalpy, the heat of reaction. And delta S naught is our change in entropy, which is a measure of disorder. So again, for the reaction that we looked at before, and I'm just going to go ahead and show you the page from the text here. I have a delta G of minus 44.8 kilojoules per mole. Our delta H is minus 84.1. Delta S is minus 0.132 kilojoules per mole Kelvin. And then there's our equilibrium constant there. Now, what does this tell us? What do these values tell us? Well, for one, we have a negative delta G. That means that our reaction is favorable, that we would have more product than reactant at equilibrium. We also see that with the equilibrium constant. That's how much free energy is released when the reaction occurs. We release, because it's negative, 44.8 kilojoules per mole. Now, part of that is released in the form of heat, delta H, so 84.1 kilojoules per mole. And then our delta S is also negative. What does that mean? Well, that means that entropy is released. You can't release entropy. When delta S is negative, you have a decrease in entropy, which is a decrease in disorder, or an increase in order. Qualitatively speaking, we can see that entropy has to decrease in this reaction. How do I know that? Well, I've got 1 mole of stuff here, 1 mole there, so 2 moles and just 1 mole on the product side. Specifically, that's for gases. This is a gas, that's a gas. So I've gone towards the side with fewer moles of gases, which means my entropy has gone down. More moles of gases is greater entropy. So I might be releasing a bunch of heat, but because it takes up some, we lose some entropy, our overall energy change isn't as great as just the enthalpy change. So I wanted to show this to you, not to just throw a lot of numbers at you, but if we drew a diagram here, and we have delta G naught, we would have, let's say we'll have our reactants and our products. And now we've got our energy difference between these two is our delta G naught. Actually, I should not call this, this would just be G naught, I guess. We'll just call it energy. So my energy difference, free energy difference between reactants and products is our delta G naught. Now, oftentimes for organic reactions, we don't get a big entropy change, so we could substitute enthalpy for energy, substitute delta H for delta G, but it's more correct to talk about our delta G, our free energy change. All right. So what else can I say about this little diagram here? Well, my x-axis is what I'm going to call the reaction coordinate, and it just means that, you know, here's the start of the reaction, here's the end of the reaction. We're moving along in time, effectively. Now, one thing that this doesn't tell us is how we got from reactants to products. So thermodynamics tells you where you started and where you ended up, relatively speaking, but it doesn't tell you how you got there. And that's where we're going to look at kinetics. And in the realm of kinetics, we're going to look at rates of reactions. So how fast reactions occur. And another way of looking at it is we're answering the question how likely reactions are to occur. I'm abbreviating reactions RXN here. And these are typically going to be given by a rate law. And so let's say we had the following. Let's say we had CH3Br plus Cn minus, and that goes to CH3Cn plus Br minus. Our rate, which is going to be defined as minus delta CH3Br over delta T. So that's, I put a minus here because we're going to be losing it. So it's going to be the change in concentration of, in this case, bromomethane with respect to time. And that's going to be equal to some rate constant. This is a lowercase k. Make that apparent here. Lowercase k times some combination of concentrations of the reactants. These are empirically determined. Rate laws are empirically determined. Okay, I can't look at this reaction and say, yes, that's going to be my rate law. How do I know that? Well, let's look at a similar reaction. CH3, 3Cbr plus Cn minus gives me CH3, 3CCN plus Br minus. Here my rate, which is minus delta CH3, 3Cbr over delta T, that's K times CH3, 3Cbr. So I only have a concentration dependence on one of the reactants in this other reaction. So you actually have to do the reaction and measure its rate in order to come up with a rate law. And this is stuff that you did in Chem 1B. But we'll take a look at this maybe a little more closely when I talk more about, well, these reaction progress diagrams. So, I have my reaction, I have my energy, and, I start with my reactants, end with my products. And what kinetics is going to look at is how we get there. Kinetics is going to look at this part here. And that is a little sloppy. That should be a little more gradual curve. Let's scratch that out there. So kinetics is going to be the realm of this. Because in order to get a chemical reaction to occur, we have to have two molecules bump into each other, usually. Maybe sometimes it's just one molecule falling apart. And the molecules have to collide with enough energy and enough orientation. Well, that energy here is what we call an activation energy. And that's how much energy we have to add to the reactants to make them react, and then they'll react to products and release energy. So in this case, we have a net release of energy. So our products are lower energy than reactants. So our delta G naught would be negative. But we happen to have this big energy hump that we have to get over. So this might be a slow reaction. A smaller hump would be a faster reaction, and a larger hump would be an even slower reaction. And we'll take a look at these types of diagrams in more detail in a couple of lectures. But for right now, I wanted to show you thermodynamics and kinetics, the difference between what the two are looking at and really what we're dealing with. Okay? All right. Well, until next time, stay safe out there. Bye now.